Okay, last time we had finished up with naming of ionic compounds made of monoatomic ions. Now today we're going to talk about a different kind of compound, covalent compounds, and because they are put together differently, we have a different set of rules for naming them. So covalent compounds form when the high ionization energies of the molecules can't be overcome by the lattice energy. The atoms in a covalent bond, I need a periodic table. Okay, sorry. I was just thinking I can't walk over there. The atoms in a covalent bond are sharing electrons rather than transferring them. And the reason for that is because of the high ionization energies. You remember in the last chapter we talked about ionization energies. That ionization energies are increased going across and increased going up. So if we make a compound out of two nonmetals, the things in this area, then what would happen is, in order to make it be an ionic compound, one of the atoms would have to become a cation and one would have to become an anion. And the ionization energies would be so high to form that cation that you couldn't overcome it with the lattice energy. And so for that reason, we can't make cations and anions because there has to be a net lowering of the potential energy. So we make discrete molecules. Now, I think I showed you these before. My examples of sodium chloride and of water, right? I showed you these before. So we think of these water molecules, H2O, being quite different because this is one water and this is another. And this is representing a lattice that's big that goes out in three dimensions all around. So when we have a discrete molecule, we can name it differently. Here we use the smallest whole number ratio, sodium chloride, 1:1. In this, we actually name what is in the individual molecules. So as we think about this, we want to talk about why they're different. First of all, the molecules form and they follow the law of definite proportions and the law of multiple proportions. The law of definite proportions says this: if you have the same compound, then you have the same mass ratio. So what does this mean? It's easier to see in an example. If we have water, H2O, okay, we're going to have 2 grams of hydrogen and 16 grams of oxygen. It'll always be in that ratio, and if it's not in that ratio, then we don't have water, we have something else. Okay, now the law of multiple proportions goes off from this. It says that elements that can form more than one compound, like hydrogen and oxygen, can make water and they can make other things, form more than one compound. Will combine with their masses in small whole number ratios. Now, when you look at this in writing in words, it doesn't make any sense at all. So you have to look at an example, small whole number ratios. Have to look at an example for it to make sense. So we looked at water, H2O. It has 2 grams of hydrogen and 16 grams of oxygen. Let's look at hydrogen peroxide. You know this because it's at home in your medicine cabinet, right? And if we look at hydrogen peroxide, we'll have 2 grams of hydrogen, but we'll have 32 grams of oxygen in there. So now when we look at this, in water, I have 2 grams of hydrogen. In hydrogen peroxide, I have 2 grams of hydrogen. And 2 to 2 is a 1:1 ratio. It's a small whole number ratio of the masses. Now let's look at the oxygen. I have 16 grams of oxygen in water, and I have 32 grams of oxygen in hydrogen peroxide. So this is a 16 to 32, or a 1:2 ratio. So when this was discovered, this is what led John Dalton to figure out that elements came in little building blocks, and he called them atoms for the atomic theory. So I think that's kind of cool to think about it historically and look at how this goes together. So we have H2O, water, H2O2, hydrogen peroxide. Anybody know what's H2O for? Drinking. It's a joke. It's a joke. What's H2O for? It's for drinking. It was a joke. Okay. Now, jokes aside, when we have a molecular compound, we cannot easily figure out what it will form. With the ions, all we had to do was make electrically neutral compounds. We looked at the charge on the cation, the charge on the anions, and we joined them together and made it neutral. But it's not so easy with molecules. So when we look at the molecule, we look at